Okay. Okay. Yeah. No, is this okay? Yeah. Yeah. Okay. Okay. Thank you. Is it one or? Yeah. Oh, the point is. Okay. Thank you very much, Marco, for this very nice possibility that has been given to me to attend the school. Actually, it feels like I'm studying a new PhD. Except that this time I will have to do it with myself. But this is very refreshing and very interesting a lot. And the reason why I wanted to come and I asked you to come is because in fact, indeed, we are setting up with my group an experiment which possibly will be able to probe action dark matter. So it's kind of a like connected to quantum microwaves, but it's slightly different. I think that what has been like pursued so far. So I'm going to explain to you where we are. So not so far, in fact, but since we have kind of a bit different perspective of view. I mean, I like a different language. I will also try to establish a common vocabulary and to express how, I mean, like we in our language we let's say envision we see these things which have been done. For example, the CTV's paper. So this experience. So this is like part of my lab. I mean, you see, it's more like here you have stairs. You see that it's jam packed. I mean, it's because it's in Paris downtown, so it looks more like a submarine than the lab. And like what you see here also is that it was before the COVID era because we don't wear masks anymore. So now, unfortunately, we have to work. Hopefully, not for so long, but we have to wear a mask. And so this experiment has been set up by William Legrand, who's here. And there is a PhD student coming, Arnaud Thierry, but he's not on the picture. He has joined recently. And I have a young assistant professor in my team, Mathieu Delbecq, who's working on this. And Audrey Coté, she's a theorist with whom we have a very long-standing collaboration, and she works on the theoretical aspects of detection. Okay. So, well, I don't have to motivate this slide. I mean, it's just, I always like to show this galaxy. But I mean, of course, so the idea is to use what we have learned from the manipulation of microwave fields in the quantum limit to probe the so-called invisible actions in a laboratory experiment. And so this is what like the experiment which we're setting up is about. So, well, of course, I don't have to, again, I mean, I just have to flash this. So the actions are of course, very well motivated. So I recall here this Becky Quinn, and of course, this was very nicely introduced by Igor. And so for us, I mean, experimentalists, essentially the thing which is very interesting is that let's say the mass. So Igor was showing. I mean, again, I mean the maximum likelihood of the mass region where it should be is somewhere in the microwave range, where again we a priori know very well how to amplify the signal down to the quantum limits. Okay, and so the point is that if this field exists, it will induce. So this stems from the chiral anomaly. It will induce a coupling between the electric and the magnetic part of the electromagnetic field with a very small coupling constant here, and an amplitude which is actually quite large. It will induce a coupling which will appear as a modification of Maxwell's equation. And essentially, of course, this is coupling to fermions, but we're not focused to the coupling to photons, which is, as Igor introduced, the thing which is less dependent on the models. And so the question now is how to detect such a very small correction to Maxwell's equation. And so And so, in fact, this like CTV proposed a very elegant way to do that in 1983, and essentially the idea is that this mixing term and the Lagrangian can be revealed by if you confine the electromagnetic field between two mirrors, like or between in the cavity, and if you put this cavity in large constant magnetic field, constant time. And essentially, so the cavity mode I have sketched here in yellow. The B field is in blue. So this is again this triangular diagram with the axiom here in pink. And so essentially, thanks to that, I mean, essentially the axiom drive, if they exist. So the axioms are in spin here. They're everywhere, of course. And they populate the axioms. It's as if the cavity was connected to a fictitious port, fictitious microwave source, which would be the axiom. It would drive the cavity, and which means that if you don't do anything to the cavity, it will essentially be filled by a tiny amount of extra photons, which, if you're able to detect them, will reveal that the axiom exists. And so the thing is that it's, as again, Igor was mentioning, it's a needle in a haystack problem, because of course, the TCD doesn't tell you where the mass of the axiom should be. It tells you that it should be some range. And so, it seems this coupling constant is very small, making many experiments to have cosmologically relevant sensitivity with different cavities is actually extremely challenging. And given the very feeble signal, so this. That's right. Because if you plug in numbers, so they have very important idea. The problem is yeah, it's essentially, you see here, it's the number of photons, which if you plug in numbers and you're for realistic microwave geometries, you find some 10 to the minus 20 or something. So it's extremely small. So this is arguably a very small number, but still, since this is pretty specific, one can be like a device experiments to detect that. But it's like reaching this sensitivity for each frequency is extremely challenging.
Yeah. What is this number? This is the occupation number, or
this is the extra number of photons which you would have from the driving of the axiom. So it's extremely, if the axiom would exist. Yeah.
And that's related to my question. So that number is less than 1?
How much less than 1? 10 to the minus 20.
So like a fraction of a photon?
Yeah. So
okay.
it's essentially, so it's kind of weird to present it like this. It's just that if you imagine the cavity, which is it's on average, of course, it's an average, right? So you don't, since it's a coherent field, you can define let's say and the effect on average, which you would see if you would record for a long time. This would correspond to this value of but it's much less. Which means that you will have to wait for a very long time for a single photon to exist the cavity and to detect it, if you would do that in that way.
Yeah.
And what's the timeline of that number?
So this is in a stationary state. And then this is in a stationary state, since this field is all the time here. In a stationary state, you get this extra number of photons. So if I would switch off the coupling, and I would, let's say, have some background photon number in the microwave cavity. If I would switch it on, like after the stationary state is established, so which is essentially the line width related to the inverse line width of the microwave cavity, I will have this extra number of photons on average, which means that I will have to wait for this times essentially the coupling of the cavity to the microwave line for a single photon. So I will have to average for a very long time. The good thing is that this looks an incredibly small number, but this if you average for a long time, you can.
Right, but I guess I'm asking, is this number?
With this number, are we running this thing for a second or a day?
Yeah, so but this depends, of course, on the experiment. But yeah, this I don't exactly. I think it's for days and something like this. I don't know exactly what the other guys are, how long they are integrated. Okay, so now I mean, just to establish a common vocabulary, so I found it interesting to like kind of rederive very quickly the CQV's cavity, the idea of CQV's cavity haloscope, because I realized that we have some kind of very different vocabulary, and so well, and so it's just to make connection to what I will be talking to you about later on, which is the principle of our own cavity haloscope. So that's essentially CTV's idea. So I have the Hamiltonian of the system, which is very simple. If I am able to isolate a single mode of the electromagnetic field, which is characterized by this operator, so I quantize the electric field of the cavity in this way. So that's the standard way of quantization of the electromagnetic field in quantum electrodynamics. And essentially, I get a Hamiltonian of the single mode of the electromagnetic field, which will be somewhere around several gigahertz in our case, which is just a harmonic oscillator. And essentially, I will have to add, I mean, this the axion photon coupling term. So you see here there is the axion field here, and this is the E dot B term, which Igor was talking to us about. And then, of course, since my cavity is connected, it's dissipated, plus there are ports connecting to the cavity. There are bats, which are important for establishing the line width of the cavity and for driving the cavity. Okay, and so, yeah.
Is that integral term being added to the Hamiltonian?
This one here?
Uh-huh.
Yeah, it's multiplied. This is times, yeah.
Okay,
It's just that
sorry, I thought that was an alpha.
it's a multiply.
Okay.
Sorry. I wanted to do, like, I'm sorry, I wanted to do something fancy because everyone was writing to the blackboard. As if I would just write in this is my handwriting. But it's just, well, okay. So hopefully, no, this cross, I mean, I already identified it was maybe not super clear. Hopefully my handwriting is clearer on the other view graphs. And now if I write down the equation of motion of the field, so they just do the Heisenberg equations, I will have something which is like that, which looks like that. And what you see, what you see here, is that this is like the resonance frequency of the cavity. So that's for accounting for the bat. So this is the dissipation. So this is the bat is just kappa. And then this is the driving term, which I was talking to you about, arising from the axion field. You see here, I mean, this. I already anticipated that I only pick up the resonant terms here, so I don't have the plus I omega A in the cosine. And if I do the rotating wave approximation, so essentially I say that the operator A is some slow operator times the driving, let's say, speed arising from the axion. In a stationary regime, I found exactly what CQV showed us. Which is this, which is that if I am adding a constant magnetic field, so this is a geometrical factor just related to the volume. But if I am adding a constant magnetic field to the cavity, and I have the axions here, I will have an extra number of photons inside the cavity due to the axion field. And of course, this will be maximally efficient. Yeah.
Thanks. What does it mean that A is slow? Is it slowly evolving in time?
Yeah, it's because in this it's the rotating wave approximation. I essentially factorize the oscillations which are the source term in this differential equation, and I say that the rest of the time dependence here is slow with respect to this fast oscillation.
Okay, thank you.
And you see, and this will be valid. I mean, essentially, as long as you're not completely off resonance with respect to the cap. This is the resonant approximation. And so this will be maximally efficient. So this is at the cavity, when the cavity frequency is resonant with the axial frequency. And if I am able to do this, then I get the number of photons, which I can translate into an output power, like in the paper by CQV. And you see that it's exactly what it has. So you see that it's exactly what Igor was telling us. So here, this is the volume here. That's the magnetic field which is there, and this is the inverse of the quality factor. This is the inverse of the quality factor, the line width. So it's always good to have it like it. So it's actually you can essentially rephrase this expression here into the paper by CQV. Okay, so this is a slightly different way of expressing the stuff. It's like that. And so then, well, I just like this is kind of an old stuff which I found. I mean, and so this is kind of this kind of 2D plot. I mean, which this is from the Quarks collaboration, which I did it on the coupling constant. It's probably it's already out of date somehow. And so essentially using this idea, I mean, there are a lot of pioneering experiments of the DMX, of course, and the haystack and the quarks. I think the quarks now they have gone, I mean, a bit further down. So the thing is that so you see you have except that ADMX, which is keep on moving here, like there are of course very narrow lines, and the reason why is because essentially it's always this, right? You have to find a matching condition, and the line width on which you're able to probe this potential coupling is just this kappa, and since you want to have kappa small because you want to have larger sensitivity, you cannot have a large line width. That's always a trade-off. Okay, and so here's our idea. Well, so our idea, I mean, is at the beginning it looks like it looks like more or less similar, but in fact it's there are some differences. So our idea is to say, okay, if I want to do away with this needle in a haystack problem. In fact, in Kontos, this would be super cool. I mean, if we had a broadband, let's say, detector. So let's try to make a broadband detector. So how can I make a broadband detector? I need to find a way to not to have a constant magnetic field. Like let's say it would be super nice if we had not a constant magnetic field, but if we had a magnetic field varying in time, like oscillating in time, in fact. And this is actually what you have if you place a magnet in a magnetic field. So if you place a magnet in a magnetic field, you have a phenomenon called the ferromagnetic resonance. So these are magnetic excitations, the magnets, which there are collective modes arising from the fact that you you have a macroscopic magnetization. And these collective modes, I mean, they process around the extramagnetic field. That's called a T-tail mode. It's a long wavelength procession. And actually, they can be pretty narrow. So they are used, in fact, as microwave passive filters, microwave components. So you have ferromagnetic insulators like the yttrium aurium garnets, which can have quality factors of about 10,000. And the one we also have anti-ferromagnets, so it's slightly more complicated, but it's exactly the same idea, which can have pretty large quality factors. But the nice thing is that just now, essentially, these resonances are tunable, so it's you can tune them just by an extramagnetic field over a very wide span. So it goes like essentially 28 gigahertz per Tesla, and this is 1 Bohr magnitude. And this means that by applying a magnetic field which is rather moderate, so between let's say 1 to 3 Tesla for the simplest case, you can essentially span the region where essentially even again we're reminding us today that they have the maximum likelihood of the accident. Yeah.
Like,
This may be a little bit out there, but if a magnetic monopole existed, would you be able to see it using this technology?
I don't know.
Okay.
We have to.
Okay, no worries.
Yeah,
thanks.
yeah, you would have, maybe, it would be interesting to, see what we have in mind. I don't know, we would have to discuss, I would be happy to discuss this with you.
Sure, thanks.
Okay, and so this is tunable in a range between, let's say, 1 microvolt to 100 microvolts. Just by changing a knob, I mean, which is like an easy knob, let's say, in a laboratory, which is a magnetic field. And it's not a very large magnetic field, so it's a potentially a broadband held screen. Okay, so again, I mean, but I promise I will not, because I'm running late anyway. So again, I mean, we can start just to write down, I mean, like exactly a bit like we did with the CKB, we write down the Hamiltonian. So there is the electromagnetic part. There is the magnetic part now. So you have a coupling between the magnetic moment and the magnetic field. And you see that here, that's important. You have a coupling between the photons and the magnets. Plus, you have also the ferromagnetic resonance here, which is built in. And again, you have this action term, but now the action through the fact that now the magnetic field is not only given by the laboratory field, but also by the magnetization. You have direct coupling between the magnet, let's say the magnetization, and the electric field, which can be revealed by the axons. This is why I had sketched, you see this a bit like this. I have now the red mode, like this is a magnetic mode, the cavity photons. And instead of having E dot B, I have E dot M. And now the M is actually going to process at a frequency which will be tunable. And you immediately see what will happen. Because here now I have a nice, like a combination where essentially this frequency, let's say, for example, minus this one or plus this one will be commensurate with, will be equal to omega A. And this will be my new resonant condition here. Okay, let's move on. We'll see how it works. Okay. And so now I can simplify this Hamiltonian. I write down the cavity Hamiltonian. So now the precession, the ferromagnetic resonance has also some harmonic oscillator nature. And so I have now two modes, one magnetic mode and one cavity mode. They are coupled through this B dot, so M dot B term like that. So this is the coupling. This is and essentially in our case we will drive them through the microwave cavity, and then I have here this H axiom gamma gamma, which is the axiom for coupling term. One thing which is very important is that I want to add a new twist, it's kind of a bit like with drawers, this setup. So I apologize. Because here I have, like, I would have two linear oscillators coupled together. So it would not, so we know that we need to add some unharmonicity, a twizzle of unharmonicity. Let's say if we want to get nice, like if you want to go, I mean, to have interesting amplification properties. And so here I assume that now the photons, I have made them interacting thanks to this curve term. And this I can do this by adding a superconducting circuit in a microwave cavity. You will see how it looks like in the experiment. Okay, so this is what I assume. Okay, so again, so now I mean I can so I have two coupled system, and I can diagonalize the Hamiltonian without just for the two oscillators. And what is important, why I'm showing this to you, is because this is a very interesting way to characterize the coupling. Because this here now you have two eigenfrequencies, and they have an avoided crossing in these eigenfrequencies because you have two coupled systems. And this is the first thing we're going to look for when you measure the microwave transmission of our microwave cavity. And this will allow us to calibrate or to evaluate the G2 here. Okay, and again now this omega m again is tunable with the external magnetic field. And the first thing which we'll ask ourselves is, do we see this avoided crossing? Okay, that's a bit cumbersome, so I will just, and then you can re-express everything, of course, in a new basis. Now everyone is coupled together. It looks a bit messy, but it's interesting to see now that in the stationary regime. So now, I mean, I have like two driving frequencies, and the reason why I have two driving frequencies is because I have an harmonicity, and you will see that I will make use of that for the detection schema. And so you see now that in a stationary regime, I have similar equations as the one which I wrote down for the CTV haloscope. But these equations are slightly different because now you see you have terms here in the frequency of the two modes, which depend on the population on the other mode. And so this is very important because you remember that the axiom, if they exist, they modify the population of the given mode, right? But in the original CTV haloscope, you just need to measure power, just because you need to see the photons coming out, because you have a population of photons, and you see the photons going out of the cavity, and you measure power essentially. Here, thanks to this, and this you see this is related to the anharmonicity. You see there is this K prefactor all the time, or this K here. This means that now the population potentially arising from the actions, it's translated into a frequency, which is something which a priori I know much better how to measure than the power. And so that's one thing which is really important in this setup. And now the idea is that I will read down these frequencies and measure the phase now of the microwave signal. So you see that the phase of the microwave signal, which is the argument of this denominator here, that's what we measure all the time. For people measuring qubits, they measure also the phase of the microwave signal at the resonance frequency. And this is a convenient way of measuring this frequency shift. Because you see here, the phase is just the arctangent of this dissipation divided by this the frequency here. So the phase is actually very, let's say, a powerful tool to measure this frequency shift. And so this is the second step for the calibrating the detector. We should be able to see that when I modify the population, for example, of mode minus, I can see a change in the frequency of mode plus. And so, because when I change the population, you see of mode minus, this shows up here, and so immediately it changes the phase of the mode plus. So this is the second calibration that will show you this in a specific measurement how it works. And so then we can play the same game again. So this is in a rotating frame. So I have essentially I look at all the terms which have to be stationary. So slowly evolving. So meaning that essentially this exponential here have to like the argument in exponential have to be 0. And so you see that there will be a resonance condition here in this term here for omega 1 plus omega 2 close to the action mass. So and remember that omega 1 plus omega 2 are both close to the new eigen frequencies of the two modes. So which means that now, by just changing the magnetic field, I will have a moving in scanning. Let's say I will be able to scan, over a large mass range, and to search for potential resonant interaction between the plus and minus modes, so the sum of the two modes, and the action frequency. And the nice feature of this is that it depends. So of course, on the power of the two driving terms. So this is interesting in order to. Okay. And so the cool stuff here is that if you plug in the numbers which we're targeting, so it's a Kerr nonlinearity of 100 kilohertz. So we can populate with quite a large number of photons. Yeah.
Sorry, what was that K variable? The big K?
So K is the interaction which I have built between the photons in the. Wait, it's not. So this is a little twizzle or the twist which I have added to this. So I have made the photons interacting inside the cavity by adding matter by a superconducting circuit. So that's another interesting ingredient which is not present in the other, let's say, haloscopes. So that's the interaction. That's a 4-point interaction. If I just quoting and bond line. And so this we know very well how to engineer because matter gives a nonlinearity and so, yeah. Okay, and so now if you plug in numbers, so this is the delta. So this is again a very small number, right? But if we have a large pumping in a microwave case, so we can populate by a large number of photons these microwave cavities, plus a large anharmonicity. You see that if we reach the resonance condition between the axons and these two modes, we can get what I call a macroscopic. Well, 1 kilohertz is macroscopic, right? Like frequency shift, which will turn into a macroscopic phase shift, so some fractions of radians, but which can be detected easily. So easily is with quotes, of course. It's just because we haven't started completely to do a run of measurements that we say that it's easy. Of course, we know that it's not easy. Okay, so how does it look like in practice? So what we have started to work. So this, well, actually, it doesn't look so impressive. So it's just a chunk of copper with a hole in it. And so these are microwave lines here. So here in this design, we have two additional lines for driving directly the magnetic mode, but it finally ended up that it was not useful in this first. And so the fundamental mode of this cavity will be around 7 gigahertz. And so this is one of our dilution refrigerators. So so the measurements are going to be carried out at 20 millikelvin. And you see that there are stages here. This is 20 millikelvin. Here the stage is 100 millikelvin, 600, 1.5, and this is 4.2. And so here, well, you have like a whole. This is a whole like a bunch of wires. And so here we have a cryogenic amplifier, which has a very a low noise amplifier. It's not quantum limited, but it has a pretty low noise. This is how it looks like. So this is like a bit you see this on the right hand side of the photo at the beginning. This one, and this you see it's centimetric, right? So it's 10 centimeters. This is normal because this is it's like several gigahertz or like centimetric waves and so on. So that's the typical size of this scale. And so if you open it, so this is a slightly different design. So this is a zoom, a close up on the inside now. So you see this is 1/2 of the cavity. So it's what is called a loop gap cavity. So this is the antiferromagnetic crystal here of gadolinium vanadate, which is the one which we use in the measurements I'm going to show. So this one is interesting because actually it has there are two sublattices in magnetized and in antiferromagnet. And essentially you have two modes, one going down and one going up, and with the slope of around like this 28 gigahertz per Tesla. And essentially for this particular one, it starts at zero field at 34 gigahertz and goes down. And so there is another one going up from 34 gigahertz. So which means that if we can access this the upper branch and the lower branch simultaneously, we can span, I mean, really between several gigahertz to 100 gigahertz. And so here, this is the small piece here. You don't see there is a superconducting circuit. That's an array of squids, and that's a squid array, in order to which is in principle reducing our harmonicity. But it doesn't work so well. We're still, I mean, improving it. But nevertheless, we can still do measurements, and this is the way we do the measurements. So I just it's kind of an optical table. The most important thing here is that we have a microwave source, and we have several demodulation stages here. So we split, and then it goes down to. So this is a 2D cavity, but it works the same for 3D cavity. Then you have the microwave amplifier here, and then you have microwave amplification lines here with different microwave components, filters, circulators. And what is important here is that you have a quadrature mixer, which allows you to measure both quadratures of the electromagnetic field. So you detect the in-phase and the out-of-phase component of the electromagnetic field, which means that you are able to measure both the amplitude and the phase of the transmitted microwave signal. And okay. Okay, so let's see whether we see the resonances first at low temperatures. So in fact, this is a two-mode cavity. So that's a transmission between 5.4 to 6.6 gigahertz at 20 millikelvin at finite magnetic field. So you see here you have essentially one big mode here around 6.3 and another mode which is at 5.5. And it's fully consistent with microwave simulations, which we have. Yeah.
I don't quite understand what we're looking at here. What kind of data is this?
This is the transmission of the microwaves through the cavity. So that's if I send a photon, it tells me what is the probability for the photon going out. And so if the photon hits the right frequency, the resonant frequency, it has a very high probability of going out.
So,
Yeah.
so if an axion, oh, sorry, I forgot.
If an axion were detected, what would that look like on this plot? Just a larger spike?
Yeah, just a tiny, yeah, exactly. Yeah. If it was resonant here, yeah.
Okay, thanks.
Exactly.
Can I ask you something as well? I'm confused by the maybe I didn't quite catch that, but the Q factor for such a 5-6 gigahertz. This is not the Q factor of the copper cavity, is it?
Yes, it is.
Why is it so low? I mean, 1,000 you can do better, no?
Well, I mean, it's because well, this geometry of the cavity is has like around like 1,000.
The crystal is inside.
The
I
crystal is
understand,
inside.
right,
The crystal also
is-
modifies the
yes.
polarity factor, but I mean, not really, like how much you can get here, like depends on the purity, of course, of copper.
I would say at these frequencies, few thousand at least, no?
Oh yeah, no, okay, yeah, but not 10,000. This is I thought you wanted to have 10,000. Okay, yeah.
I mean, you can.
No, but I mean, it's like I think it's about 1,000. So like I don't remember exactly. It's maybe a bit more than 1,000. But it is true. That's so the crystal dissipates. In fact, yeah. Also, yeah. Okay. And so. Okay, and so if I now apply magnetic field and I track these resonances, this is the frequency as a function of magnetic field. You see a line going down here, and you see here that that you have like and you have the line also going down here. You see here, like you have two avoided crossings, and this is the two avoided crossings of the which I was talking to you about in the beginning when we diagonalized the two couple Hamilton. So this allows us to show that actually the magnons and the photons are actually coupled, and from this splitting here, you can estimate, or you can of course fit. I mean, the coupling strength it's about 1 gigahertz, so it's a very large coupling strength. So in our jargon, it means it would be called the ultra strong coupling regime. And we don't like and because you see the coupling strength is comparable to the frequency now of the it's much larger than the dissipation rate, but it's also comparable now to the bare frequencies. And so this is very important because this means that now you see I have now an effective cavity which is now tunable and over now a frequency span which is about 1.5 gigahertz. And again, I mean, this is what we want to have at some point because we want to have a scanning, let's say, haloscope visual, so that we don't want to potentially to play the game of haystack, etc., by just moving along this line. Okay, then I told you that the second, let's say, the second, let's say, step for setting up the experiment is actually to show that I can excite the system at a completely different frequency of the one I'm reading out the system. So this is now the phase now of the microwave signal, and I'm done.
Just before you move on.
Yeah.
On the previous plot, can you explain the red lines?
Yes, so
The red lines.
Yeah.
Yeah, that's
do they show the expected position of the resonance? Why are there deviations between the red curve?
yeah. So this is yeah. Thank you for this question. So it's because in fact there is a complexity which I didn't want to get into, is that in this region, in fact, there is a magnetic field induced phase transition of the antiferromagnet. So where essentially you don't have a antiferromagnetic order here. This is called the flip-flop phase of the gadolinium and vanadate, where essentially you start to have disorder spins, and then you get again like a ferromagnetic or a ferromagnetic phase where all the spins are aligned by the magnetic field. So this is this red curve is assuming that you have a perfect antiferromagnet all the way down there, which is of course not true. And what is important is that the red line here is actually is above. I mean the experimental data up to this area here, where we know that it will fail because we don't take into account that properly the flip-flop transition, where you have a lot of spin waves and disorder magnetic. So this is why it's not. But then here and there, here it's overlapping, here and here less, because this is close to the flip-flop, but here and there these are more or less overlapping. Here it's crappy, but this is normal because we don't take into account the flip-flop with this red curve.
Question here in when you measure the mode of the cavity in one of these points, can I say that this mode has hybridized with the?
Absolutely, yeah, that's exactly the point. This is the point of the anti-constant, the body constant. Here I have completely hybridized mode. I mean, so I read it out from the cavity, absolutely. And the reason why I see this for a long time is because I have this ultra-strong coupling, which means that the magnon is very much photon-like, far above, I mean, the photon frequency. Okay, so and so again, I mean, the second thing is that whether I can read out by measuring at the phase at the microwave frequency at the omega plus, whether I can excite at a much completely different frequency and see a resonance arising from the magnetic resonance, but far above. And you see that we start to see some feature here, which is this line here. So we see another mode, in fact, of the cavity, which is at higher frequency as well. And essentially, the contrast here is limited by the fact that the big K, which we wanted to have 100 kilohertz, is not yet at 100 kilohertz, it's much smaller. So this contrast here should be much larger, but nevertheless, you see that the principle which I explained to you works because we see it at a completely, now we excite at around between 13 gigahertz and 16 gigahertz, and we read out at 6.2 gigahertz. So we really have this nonlinear process. Okay, so sorry, yeah. And again, you see that I can follow this line here over a pretty large frequency span, which can in turn become the mass scan range of my future haloscope when I will be running the experiment with everything working together. And of course, we can anticipate that since we can follow, I mean, this line here at zero magnetic field is somewhere at 34 gigahertz, and it goes down at around 1 Tesla down to 6 gigahertz. I should be able to follow from 34 gigahertz to 6 gigahertz the line, and having in the simplest experiment, like in the first set of experiment, how it's called working in this frequency window. Okay, so then it's that's again I show this we can. So now I mean look at for this kind of very large expected let's say frequency shift, given what like how we can measure these shifts and the phase sensitivity which we have usually in our conventional setup. Well, it's going to be pretty bold, okay, but okay. We can expect to cover this. And in fact, the fact that there is a slope is because the K, you see, there is a slope because it's not on purpose. I mean, it's because this K here now. You see here there is this G square over. I mean, the driving. There is this V here now. The V is related to the detuning between the cavity and the ferromagnetic resonance. And since this change with the frequency, we see here, no, it's not here. Then, of course, the sensitivity, yeah, exactly. The sensitivity changes with in principle, with the frequency. It's inversely proportional to the frequency. At higher frequency, you get less sensitivity. So you can, okay, but that's pretty bold. So essentially, it's just plugging what we know is needed for getting a signal to noise ratio of 1 in this kind of experiment, which is in like in 1 of the minute for a frequency scan, because we have a large coherent field and we detect the phase, and essentially the mass range scan allowed by this ferromagnetic resonance, which you can track, I mean, because you have a very unharmonic like Hamilton. Okay, thank you.
Any questions? Questions or comments? Yeah.
They have questions, they should ask.
Anybody wants to join the group? Experiment?
In which, okay. The questions one is, what is the noise you assume to get this prospect?
Yeah, the noise I assume here essentially the fluctuations of the coherent field, like the Champ noise, let's say, because I have a coherent field, so which limits, which in fact tells me how much the phase will fluctuate during the measurement, the phase of the microwave signal, and so this is just n bar. This is proportional to the since it's a coherent field, it is proportional. The fluctuations are proportional to the number, or exactly to the number, in fact, and so this is what I assume, and it's fully consistent to what we, let's say, have in the lab. I mean, when we so you can translate this frequency shift into a phase shift, which is some 10 to the -3 radians, let's say, something like this, and this is consistent with the noise, let's say, of the amplifier. This is more or less what we need, I mean, to get a signal to noise ratio of 1, like several limits to get a signal to noise ratio of 1 for one scan, essentially one. If we do frequency scan to resolve the phasing.
Has this translated into number of photons in the
Exactly, the extra number of, yes, exactly.
the cavity, or
Yes, exactly, yeah.
you are really operating de facto in beyond the quantum limit?
So here it's, I think it's fully, it's just that since we have a large coherent field, essentially the phase is very well, let's say, so we have large coherent, so we have large number of fluctuations. But then since we have large number of fluctuations, the phase is very well defined, the phase of the microwave signal. And so this is fully consistent with what is known for quantum amplification. It's just that since I have a large pump, essentially, and I do phase detection, then I can have a large sensitivity. And so it's and then of course I haven't talked about like that you can, in fact, this is so where you can actually go even further is that this unharmonicity which you have here, that's the lowest order effect of the unharmonicity. But of course, if you now pump even more, and so this has been worked out by Clerc and Laflamme into PRA 2011, I think. This can go to an instability, to an unstable regime, like because you have the quartic potential of the photonic Hamiltonian, and this can are the basic ingredients for making a quantum limiting amplifier. So this is not surprising that if you have this kind of unharmonicity, you can get very good figures of merit. It's kind of a built-in in situ amplifier. I don't have, let's say, to create the photons from the actions in one part of the experiment, is to take them out and then to measure what happens with the amplifier, and just create them in situ and detect them in situ.
Okay, so there's a question online from Joachim Kopp. He says that he didn't understand which coupling of the axiom this method is sensitive to in the end, the coupling to the B field by the Primakov interaction or the coupling to the fermions in the crystal.
Thank you very much, Joachim, for this question. So, in fact, this is kind of the coupling. Now, what I have done is a coupling to the B field. But since now I have a magnetized material, it could be also sensitive or extremely sensitive, in fact, because they have a huge internal field to the coupling to the fermions.
That is the field in the crystal that is oscillating.
Exactly.
External field.
No, it's not the external B field. It's both the field of the crystal which is oscillating and the internal field from the magnetic material arising from the spin polarization of each of the two sublattices. So in principle, I'm sensitive to both, but since it's now it's the most, let's say, accepted like a coupling is the photon coupling. So the coupling to fermions, I mean, it's kind of a bit less clear. I mean, how it should behave. So, yeah. But in principle, it works also with this.
Actually, I have a couple of more questions, but I wonder if we just should stop here and take a break, and then we can discuss it. Or unless there's a question from the audience. Also online, I can see. So thanks again, Takis.